And welcome back. We are working today on section 6.4, Introduction to Continuous Probability. In this first video, we're going to try to tackle this first learning objective. We're going to examine random variables and probability density functions. It's a mouthful. So to get us sort of in the probability space, if you'll pardon the pun, which makes no sense to anybody, we'll first just kind of give a bunch of definitions to get us in the ballpark. So essentially, we're going to imagine that what we're working on is an experiment, which is its own definition that we could discuss, but a situation in which some activity, exercise, etc. is repeated. So we can imagine that one result of this experiment, one thing that we could study at the end of it, we'll call an outcome. The sample space would be all of those possible outcomes kind of put together in one package, just a list of all of these things. An event, which sounds a lot like an outcome in English, they could be considered synonymous, but an event could be one outcome or it could be several outcomes kind of put together. So it's any combination of things in the sample space. And then a certain event is sometimes labeled with this null set symbol. And then the impossible event is the one that corresponds to no outcomes within that sample space. So a certain event would be, again, basically the entire sample space, something that has to occur within the given scope. An impossible event, something that could not occur within the possible scope. I'm going to put a little asterisk on those things because once we hit the continuous probability stuff, it's a little bit weirder. But that for the discrete case, for the list of possible outcomes, that's what we're going to think about these two certain and impossible events looking like. So just to get us kind of in the mode, we'll pick the discrete case, although, again, this section is called continuous probability, so we're going to move pretty quickly to looking at infinitely many options. But if we look at the case in which there's just a finite list of them, we'll consider our experiment to be the following. We'll roll two six-sided dice, so the numbers 1, 2, 3, 4, 5, 6 on each potential side, and then we'll add the faces, the two numbers on the faces shown. So we could roll a 2 and a 3, we'd add those together and get a 5, for instance. So to explore our definitions, the sample space would be whole numbers from 2 through 12. We couldn't go lower than 2 because you'd have two six-sided dice, so the lowest number on one could be 1, lowest number on the other would be 1. Adding those together would give us 2. And then correspondingly, the largest possible sum would be 12. That would be 6 plus 6 on the two dice. So, and then we can get everything in between. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So one outcome, one potential thing that could come out of this is you roll the two dice, you add them together, and the outcome is 7, because that's what the sum of those two faces could be. We could talk about an event that is more complicated than a single outcome, so maybe we could describe the event, the sum is greater than 8, in which case that would be all these outcomes corresponding to 9, 10, 11, and 12. We could say a certain event, because there's multiple ways to phrase this, but the sum is not 1. Well, we couldn't have gotten 1 to begin with, so this is just saying all the other possible things. There's a 100% chance that the sum is not 1. And an impossible event would correspond to items that can't be in our sample space at all. So there are no combinations that end up with a sum greater than 13, because 12 was the biggest one we could get to. Okay, so moving on to the continuous side of things, because that's more where our calculus minds are going to go here. A continuous probability density function. It's a mouthful. But basically what it says is you've got some random variable. It can take on numbers other than just a list. So there could be a whole range of them, but they are real numbers. So they could be irrational or have lots of decimals to them, not just whole numbers anymore, like our last slide. And then they have to satisfy some other stuff in order for them to be sort of, think of them at the way probability ought to work. So one of those conditions is that when you look at each of the individual probabilities, so F is a way for us to take some event and for it to tell us how likely that event is. So that's what this probability density function's job is. So f of x is saying, how likely is this event? Well, not negative. It seems like no matter what event we pick from our sample space, no matter what x we choose, it shouldn't have a negative probability because that feels kind of weird. Part of that, and that's sort of built into these two things combined, but we shouldn't have a probability that's greater than 1 either. But we kind of cover that by saying, look, you've got all of these probabilities added together, and because there are potentially infinitely many x's to choose from, then we cover all these things from negative infinity to positive infinity, all possible x values. If you add up all those probabilities together, you should get 1. Another way to think about this, of course, would be not as a decimal, but as a percentage. So we could think of this as 100%. Maybe that would be a more useful phrasing of that value. But that's saying, look, if you add up all the possibilities, you should get 100%. Not too crazy of a claim. Okay, and then the last thing is the way you find other probabilities. These are kind of the extremes. You can't go negative. Everything has to add up to 100. If you want to know some probability, then basically you of the value that you've chosen, the x value being between a and b, then you basically integrate this probability function, this density function, from a to b. So you're adding up all the possible outcomes that could result in x being that number. And so f of x tells you the probability of that. So we'll do a little bit of that. We can also do more interesting stuff with the distribution function itself. So the last thing we'll do here is we'll take what we're claiming should be a valid continuous probability distribution. It's got this crazy definition, which is often the case where the interesting stuff falls on some interval, and then basically the probability of anything else is 0. So here's where that impossible event situation comes in. We don't want it to be possible to pick an x value that's either smaller than 0, so to the left, or bigger than whatever this constant is. So stuff to the right should be impossible. So really the only thing that should have any non-negative probability associated with it, any positive probability, would be an x value that's chosen on this interval. So the problem here is that we're being told this is a continuous probability distribution, which is great, but we don't know what the value of k is. So we couldn't actually compute, we couldn't know what values to use yet. So our job is to find k so that this is a probability distribution, which means we need to use those rules we were given in the definition. So one of the things we were told is to make sure that the inputs are always positive, or non-negative for the less interesting cases. And okay, so non-negative includes the 0 option, which is certainly true here. And I just scrolled to the previous slide for a second to show that if you pick an x value that's positive, there's no way for this fraction to be negative either, because you'd have a positive number divided by something that's guaranteed to be positive, because if you square it and add 1, it's going to be positive. So we sort of covered the first base there. So we don't really have to worry about the rule number 1, that f of x is greater than or equal to 0 for every x. We only really have to consider the definite integral equaling 1. That's that second rule we were given for a probability density function. So basically, we're going to set up an equation that looks like the integral of all of these f of x's, because this is how you find probability, and we want to make sure that all these things actually do add up to 100%. That's basically the only thing that can go wrong with this so far, and we're being told that this must be a probability density function. So we ought to be able to set this up and only have to look at the interval where that interesting fraction takes over. We're being told that if we're to the left of 0 or greater than k, then this integral is 0. So we don't really have to add all that up. We could just integrate from 0 to k for this formula that only works between 0 and k and make sure that it's equal to 1. So what ought to happen is that on the left side here, we'll fall out some expression with k in it, and we can use it to solve for k. Okay, so this feels weird, but we're going to make it happen. Our integral was not computable just using our standard kind of strategy, so we're going to pick a substitution, and that's going to give us, so here is u. We're going to replace that bottom piece with our substituted value. And then we've also got the substitution part that corresponds to the derivative, these differential substitutions. So this piece is where dx is going to get replaced by that fraction with du. And we sort of get lucky in this case because our x's will cancel. We've got an x there, and then we'll have a half that comes out in front. But other than that, the only stuff with variables in it is 1 over u. And I'm following through on that standard strategy of once we go to the substitution, reminding myself that these limits of integration correspond to x values, not to u values. So we'll use that convention of x equals 0, x equals k instead of just 0 and k. But really, we're in great shape here because this is an integral that we're getting pretty good at. Remember, I can't use power rule, but we do have a special strategy for this where the integral of 1 over u is natural log, in particular natural log of absolute value of u. And just to recall, this 1/2 was just kind of floating out in front because that was part of our substitution. So rehashing, this was the integral we set equal to 1. It turns out that integral is actually this, 1/2 natural log of absolute value of u evaluated at these two things. Let's go back to our x's before I make some sort of crazy error where I plug in k for u and 0 for u, because that shouldn't happen. Go back to our x's. These are the things that k can get and 0 can get plugged into. So k goes in for x, 0 goes in for x, and we can get rid of the absolute values here because, again, if you take a real number and square it and add 1, it's definitely going to be positive. There's no way that these absolute values have to rescue us from accidentally taking the natural log of something negative. But this is an equation that we could have been given back in our pre-calculus class. We have to solve for k because remember that was our goal like 5 minutes ago or whatever. So we can solve for k using exponentiation. So we can do e to the, so I'll do this extra step here because it's not actually on the slide, e to the second power by sort of either using the definition of the natural log or thinking of like exponentiating both sides, e to the left side, e to the right side, same deal. But then if we take away 1 and square root, I do have to remember the plus or minus in general. But in this case, remember, k was the upper side of the interval 0 to k. So doesn't really make any sense for k to be negative because that would be to the left of 0. So we're really only going to take the positive value of k and call that good. So that's it for this piece of the section. We'll be back in the next video to talk about some specific distribution functions.